Hey, welcome back, Marauders. This is section 1.1, moles and molar mass. It's my favorite section. Moles and molar mass are really important concepts in chemistry, and it's something that we're going to be using a lot throughout the year, so make sure you get some practice and understand this concept pretty well. So atoms and molecules are way too small for us to count. If you think about that penny, older pennies are made out of copper, and if a chemist wanted to figure out how many copper atoms there were in that penny, it'd be really difficult. It'd be impossible, really, for them to count how many atoms there are in it. Same thing with the water bottle there, right? If we wanted to figure out how many molecules of water there were in that, it'd be impossible for us to actually count those molecules because there's millions and billions of molecules in just that small sample of water. Fortunately, chemists have a way of quantifying how many particles, either atoms or molecules, there are in a sample, and that concept is the mole. The way we use the mole is that we can measure the mass of something. So we can find the mass of that penny or the mass of the water in that water bottle. And then we could use the concept of the mole and molar mass to convert from the mass of something into the number of moles and then into the number of particles, either atoms or molecules. So we're going to be using Avogadro's number. Avogadro's number is also called the mole. Avogadro was a scientist who came up with this concept. And the mole is a number. It's a number kind of like a dozen is a number. We know that a dozen means 12. And so if someone asked for a dozen eggs, we know that they mean they want 12 eggs. Or if they said they want 2 dozen eggs, we know that they want 24 eggs. Well, the mole is the same kind of thing. It's just a number. It's a really, really large number, but it works the same way. So a mole is 6.02 times 10 to the 23rd of something. We could be referring to atoms, we could be referring to molecules, we could be referring to eggs. It doesn't really matter, but if we say we want 1 mole of something, or we have 1 mole of something, it means we have 6.02 times 10 to the 23rd of those things. It seems like kind of a random number. Where did Avogadro come up with this? Well, it is the number of atoms in exactly 12 grams of carbon-12. So carbon-12 is a carbon atom that has a mass of 12 atomic mass units. We take that same numeric value, 12, and we weighed it out in grams. And then he found ways to count how many particles, how many atoms of carbon there were in that sample. And it ended up that there were 6.02 times 10 to the 23rd atoms in that copper sample. And that's where we came up with Avogadro's number, or the concept of the mole. Well, the good news is it doesn't work out just for carbon, but it works out for all of the elements. So all the elements have their mass numbers, right? So like for oxygen, it's 16. And it's not just 16 AMUs for one oxygen atom, but that's also the molar mass of oxygen. So if we had 1 mole of oxygen, if we had 6.02 times 10 to the 23rd oxygen atoms, it would weigh 16 grams per mole. All right, so we're going to be doing conversions between these 3 different measurements. Mass, measured in grams, a really easy quantity for us to get in a chemistry lab because we all have access to balances, into the mole, which is how we typically count things in chemistry. And then also we can convert that into the number of particles. And particles could refer to atoms if we're just dealing with an element. It could deal with molecules if we're dealing with some kind of molecular compound. It could be formula units if we're dealing with something that's like an ionic compound. And so to go from mass to moles, we're going to use molar mass. We're going to use dimensional analysis. When you multiply, the moles are going to go on top because that's the unit you want, and the grams are going to go on the bottom. We're getting the molar mass, remember, from the periodic table. So you look at the periodic table to get the molar mass. And then if we want to go from moles to particles, we're going to be using Avogadro's number. The number of particles, which could be atoms or molecules, go on top, and then 1 mole goes on the bottom because those are the units we want to cancel out. If we're going back in the other direction, we use the same conversion factors, but they're flipped around upside down so that the units we want end up on top and the units we want to have cancel out are on the bottom. So let's look at a couple examples. How many atoms are there in 3.06 grams of copper? I weighed an older penny, a penny that was pure copper, and it weighed 3.06 grams. So if I want to take that 3.06 grams and figure out, well, how many atoms are in that sample, what would I do? Well, let's take a look at this. We're going to go from grams to moles, and then from moles into number of particles. So it'll be a 2-step process. The first step, we're going to be using the molar mass, which comes from the periodic table. Second step, we're going to be using Avogadro's number, or the mole. All right, so write down what we're given. 3.06 grams of copper, and then we're going to multiply that by a conversion factor, which is the molar mass. And so I want to have grams on the bottom so that they cancel out. The 63.6 grams, that's coming from the periodic table. So I looked at my periodic table. I rounded to the nearest tenth. That's usually going to be good enough for our purposes. The grams of copper will cancel out, and then you'll be left with moles of copper, because that's the units on top. Whenever you're looking up molar mass, it's always just per 1 mole of that substance. We've got one more step. So we've gotten it from grams to moles. Now we need to go from moles into number of particles. So I'm going to put Avogadro's number on top and the moles on the bottom. So we want the moles to cancel out. That's how we know we want them on top and bottom, so that they cancel out with each other. And then Avogadro's number, 6.02 times 10 to the 23rd atoms of copper will go on the top. It doesn't matter what the substance is, this is always going to be the same. So the molar mass, this number in grams, this will vary depending upon what the substance is, and you'll need to look that up on your periodic table. But Avogadro's number, that doesn't change depending on the substance. It's always the same. Then on our calculators, we're just going to multiply all the things on the top. So 3.06 times 1 times 6.02 times 10 to the 23rd, and then divide by all the numbers on the bottom, divide by 63.6, divide by 1. And when you do that on your calculator, you get 2.90 times 10 to the 22nd atoms of copper. Really important to label all the units throughout this problem, and that way you can see that you have all the conversion factors set up the right way, and you can see what your units should be at the end, and you'll be able to set up more challenging problems later on in the year if you do include all of the units in each one of the steps. Let's take a look at another one. Similar problem, but this time working the other way. So what's the mass of 1.5 times 10 to the 24th atoms of magnesium? So this time we're starting out with the number of particles, and we want to find the mass. So we're starting over here with particles. It's going to be a two-step process to get over here to the mass. So we're going to use Avogadro's number and then the molar mass. All right, so write down what we've got to start out with. We're starting out with 1.5 times 10 to the 24th atoms of magnesium, just writing out your given information, including the units. When I do that, I know that on my next step, atoms of magnesium are going to be down here in the denominator, and the units that I want to convert it into, which is going to be moles, will be on the top. So let's take a look at that. We've got moles of magnesium on top, atoms of magnesium on the bottom. It's 6.02 times 10 to the 23rd atoms per mole. It's going to be that same number for any substance. Doesn't matter if it's magnesium or copper or carbon or anything else for a step like that. Now we have one more step, and that's to go from moles to mass. So for this step, I'm going to have grams on top and moles on the bottom. I'll find magnesium on the periodic table. I find out that it has a molar mass of 24.3 grams per every 1 mole. So I set it up like that. The units cancel out from top to bottom, and I'm going to be left with grams of magnesium. Punch that into my calculator, and I get 60.5 grams of magnesium. So similar to the first problem, but working in the other direction, from particles to mass, rather than mass to number of particles like we did in the first problem. We'll look at a couple more examples. How many molecules are there in 500 grams of H2O? So kind of an average water bottle contains about 500 grams of water. That's a half a liter of water. And so I want to figure out how many molecules are in that sample. All right, so write down what I have. I have 500 grams of H2O. And so I want to take the mass and convert that into moles. So I'm going to use molar mass. Well, this one's a little different because I'm dealing with a compound rather than just a single element. And so I can't find H2O on the periodic table, but I can find hydrogen, and separate from that I can find oxygen. And so if I add together the molar masses of 2 hydrogen atoms, because in the formula there's 2 hydrogen atoms, and 1 oxygen atom, because in each water molecule there's 1 atom of oxygen. And so if I add those together, I get a total of 18 grams per mole. So that's the molar mass of the compound water, H2O. And anytime you're dealing with a compound, whether it's ionic or molecular, you're going to add together the molar masses of the element that makes it up to get the molar mass of that compound. So again, just like before, grams are what we're starting with. So grams of H2O go on the bottom. We added that molar mass up from the periodic table. We're going to put moles on top. Then there's going to be one more step, going from moles to number of particles. In this case, our particles are called molecules because we're dealing with a molecular compound, but they're still the same number. It's still 6.02 times 10 to the 23rd. We're still using the definition of a mole. That has not changed. The moles will cancel out, and then punch that into our calculators, and we get 1.67 times 10 to the 25th molecules of H2O. So it's an enormous number of molecules in just a single water bottle. It'd be absolutely impossible to count those, and this is why chemists usually state quantities in terms of moles rather than in number of particles. One more example. How many hydrogen atoms are there in 0.350 moles of C2H6? All right, so this time we're starting out with the number of moles, and we want to go to the number of particles. So we don't have to worry about molar mass because we're not doing anything with grams in this problem. So if we have moles, we can convert directly into number of molecules by using Avogadro's number. So we've got a molecular compound here, C2H6, and there's 6.02 times 10 to the 23rd molecules of that substance per every 1 mole. But that's not exactly what this question is asking. This question is asking about the number of atoms of hydrogen. And we just found the number of molecules. Well, now if you look at the formula a little bit more closely, the formula here says that each molecule contains 2 atoms of carbon and 6 atoms of hydrogen. So I'm going to do one more step here, and that other step is that there are 6 atoms of hydrogen every time you have 1 molecule of the C2H6. I'm just getting that from the formula. There's a 6 right here as the subscript after the hydrogen, so there's 6 atoms in every molecule. And then we just multiply all the numbers across the top, divide by all the numbers on the bottom, and this is what you get. Don't forget to include the units on each one of your steps. That's all for this video. I hope you guys learned something, and don't forget to practice.